All right, let's talk about debugging. For most of us, it's that sinking feeling when your beautiful, perfect algorithm just fails. Ugh. But what if debugging wasn't this super frustrating chore? What if we could treat it like a solvable problem? Like an algorithm in itself. That's what we're going to do today. We're going to turn that guesswork into a science. So picture this. You've spent hours, maybe even days, on a really tricky data structures problem. You finally hit run and it's wrong. Or even worse, it's just stuck in an infinite loop. What do? I mean, what's your first move? Do you just start sprinkling random print statements all over the place and kind of hope for the best? Yeah, there's a much, much better way. So let's get into the core mindset shift here. We're talking about moving away from chaotic guesswork and towards a real, actual algorithm for debugging. And look, this isn't just about finding bugs faster. It's about cutting down on the frustration and actually building more robust, correct code right from the start. Okay, so look at this. This slide basically lays out two totally different worlds, right? Over on the left, you've got the guesswork trap. Come on, we've all been there. You're just randomly adding print statements, changing a line of code, hitting run, and just praying. But then on the right, you have the algorithmic method. Now, this is where we want to be. It's like operating like a surgeon. First, you define what correct even means. Then you slice the problem in half, and you keep going until you've minimized the cause down to its absolute core. So think of this explainer as your own personal workshop. We're not just here to fix one specific bug. Nope. We are building a mental toolbox, and we're going to fill it with 3 incredibly powerful tools that you can use to hunt down any bug fast, from the simplest off by one error to the most ridiculously complex logical flaw. First tool in our toolbox is the compass. We're talking about code invariance. The whole idea here is to find what's always true in your code, which gives you a fixed point to navigate by when everything else feels lost. So what exactly is an invariant? Well, let's take a loop invariant. It's basically a rule, a condition that has to be true before you even start a loop. And this is the critical part. It has to remain true after every single pass. The moment that rule breaks, boom, you've found exactly where your bug is hiding. And this right here, this is a brilliant way to see it in action. This is the core invariant for a binary search. It's a simple but really powerful promise. No matter how many times we chop our search space in half, the answer we're looking for, if it exists at all, is guaranteed to be in that shrinking space between our 2 pointers. To make that a little more visual, just imagine your array is a big number line. You've got a left pointer and a right pointer. And with every single step of the algorithm, they just squeeze inward, right? They're eliminating half of the remaining numbers. That invariant is your safety net. It's the absolute guarantee that you haven't accidentally thrown the answer away. Okay, next up in the toolbox, we have the scalpel. This tool is all about making incredibly precise cuts to the problem. It's a technique called log time localization, and it's a real game changer. A perfect real-world example of this is a tool like Git Bisect. Instead of checking every single code change one by one, which would be a total nightmare, you just tell it, hey, here's a good commit where everything worked, and here's a bad one where it's broken. Then it jumps to the halfway point and just asks you, is it good or bad here? You keep doing this, and it pinpoints the exact commit that introduced the bug with surgical precision. It's awesome. And this is why that is so powerful. I mean, think about it. If you're doing a linear search there, let's say 1,000 code commits, that could take you 1,000 tests. But bisection, it'll find that same bug in about 10 tests. That's the absolutely staggering difference between O of n and O of log n. It's literally the difference between being stuck for an entire day versus finding a bug in just a few minutes. Our third and final tool is the sieve. This is what helps us filter out all the noise and get to the heart of the matter. The technique is called minimizing failure, or you might hear it called delta debugging. The analogy here is just fantastic. Imagine your failing test case is this giant, messy pile of puzzle pieces, okay? So you split the pile in 2, and you just remove one half. Does the bug still happen? If it does, great. You can throw that other half away for good. If it doesn't, well, then you test the other half. You just keep repeating this process, splitting and discarding, until you're left with the tiniest possible handful of pieces that still triggers the bug. So the crucial point here is that this is also a really efficient algorithm. In a typical case, delta debugging, or ddmin as it's known, runs in O of n log n time. Now, Yeah, it can be a bit slower in some really tricky worst-case scenarios, but it's an incredibly systematic way to shrink a huge, scary problem into a totally manageable one. So we've got our toolbox, the compass, the scalpel, and the sieve. The big question is, how do we actually use these powerful tools in, say, a high-stakes coding interview? Let's put together an interview-ready checklist. Okay, so your code fails in the interview. First thing, don't panic. Just go through a mental checklist of the classics. Is it an off by one error in your loop boundaries, like using mid instead of mid plus one? Is your recursion missing a base case? And a graph problem, did you forget your visited set and accidentally create an infinite loop? What about integer overflow? Or maybe some funky logic in how your sliding window shrinks? Knowing these common patterns shows the interviewer you have experience and a systematic mind. And here is how you truly impress them. Don't just quietly fix the bug. Narrate your process. Out loud, state the invariant that your code is supposed to maintain. Maybe even write an assert statement in your code to prove it. And when you find the bug, explain what the minimal possible input to reproduce it would be. This just demonstrates a level of thinking that goes so far beyond simple trial and error. So I'll leave you with this final thought to chew on. The next time your code breaks, I want you to reframe the problem. Don't just ask, where is the bug? Instead, ask yourself, how can I prove with 100% certainty where the bug isn't? Because when you start systematically eliminating all the places the bug can't be, you'll find it's not just hiding, it's the only place left to look.